Well, in this session, we're going to take a look at the nonlinear restraints in Caesar 2. For many years, engineers did not consider lift-off of supports or gaps on guides or other nonlinear conditions like friction because the software or the tools that the engineers had to analyze these systems were incapable of manipulating that much data. Well, since Caesar 2 was first released over 25 years ago, there were nonlinear restraints in the software. We'll review how they work in the program and then also take a look at convergence in Caesar 2 and also how these nonlinears affect the code calculations. So we're going to take a look at the nonlinear boundary conditions in Caesar 2. Well, here's a list of different types of restraints that we have in Caesar 2. Here I'm showing symbols. Now we all can interpret these symbols. This is my symbol for Earth. I can't move Earth. It's connected to the pipe. That's an anchor. All 6 degrees of freedom. Can't move them. Here the pipe cannot move in the y direction. Here the pipe cannot move in the horizontal direction perpendicular to the pipe. These are all linear restraints. It doesn't matter what direction you pull it, left or right, you get the same stiffness out of the support. Here's a spring support with a given stiffness, so I can pull this left and right and it will load up the pipe because of that motion times the spring stiffness. Or this last one here, a limit stop. Same direction to run a pipe. So we have lots of these restraints in the program. These are all the different types, and some of them are linear, and some of them are non-linear. Okay, here's a plus Y support. The pipe can rest on the support, or it can lift off. So in the Y direction, sometimes the support is active. It wants to push down. But if the pipe wants to move vertically upwards, it is free to do so. That's the non-linear situation. Here is another guide on a piece of pipe, but this has a gap on it. There's a gap equal on either side, and the pipe is free to move until that gap closes. At that point, now the restraint becomes active. You can get more complicated. Here's a plus X restraint, saying the pipe is free to move in the positive X direction. But if it wants to move in the negative X direction, this gap must be closed first. So it is linear going to the right, and linear going a little bit to the left, but after that it changes the stiffness with that support. We have a bilinear stiffness in Caesar 2. Following the direction X with a digit 2 means it's a bilinear X restraint, meaning we have 2 different stiffnesses associated with that restraint, K1 and K2. This is good for modeling ball joint, where these are rotational stiffnesses. So you have a certain stiffness until you get a certain load, then it breaks free. So you specify the initial stiffness, the final stiffness, and the break point, the force where you go from K1 to K2. The last one I show here is a plus Y restraint, plus Y rod restraint, meaning that the pipe, instead of being able to move in the plane, the XZ plane, it instead has to follow this arc, this sphere of free motion pivoting about a pin up above the pipe itself. So you specify the length and the arc, it'll develop this arc for you. So those are different types of restraints in Caesar 2 that could be either linear or nonlinear. So what do we mean when we say it's a linear restraint? Well, here we show a piece of pipe that is connected to Earth by way of this spring, and the spring has no preload on it. There's no load when it's sitting there cold, and that would be this point right here. This plot here is load versus deflection. Now, the spring rate is our relationship between load and deflection. If I want to put more deflection in the Y direction here, up or down, I'm creating a load on the pipe. So if I pull it up, I pull the spring out. If I push in, I push the spring in, and I get a load no matter which way I go. That's changing load based on position. So the spring stiffness is a constant value. That's a linear restraint. We have a straight line here, a single line. All the nonlinear restraints do not have that condition. A nonlinear restraint does not have that constant slope. Here is a plus Y support. If I want to move in the positive Y direction, it is free. I get no load. Just move up freely. If I want to move down, I can't move at all. It is so rigid. Okay. Here is a guide with a gap. Again, it is no longer a straight line. It is no load until we close the gap, and then the load gets very large and no more displacement occurs. So that'd be an infinitely rigid stiffness once the gap is closed. So those are illustrations of the stiffness changing as a function of position. That is a nonlinear condition. Now, in Caesar 2, you can model these restraints by clicking on restraint, specifying the node number and the type. And the different types will give us either linear or nonlinear conditions. If you do not specify a stiffness, the program assumes that it is a rigid restraint. Now, in a computer program like Caesar 2, we have to specify a value, and we put in a very large stiffness for this rigid restraint. In fact, here we see the value from our configuration file. Default translational restraint stiffness is 1.75 e to the 12th. That's in newtons per millimeter, I believe, and that is very, very stiff. Most structures that you could possibly construct will have a stiffness smaller than that, but normally in piping systems where strain is a major concern, being stiffer is being more conservative. That's not always true in all situations, but in terms of thermal analysis, yes, being stiffer is more conservative. So this is a conservative approach. So here we have a Y restraint, no stiffness specified, so it is a rigid restraint. Now, how do we put that in our stiffness matrix? We have another set of presentations on the stiffness matrix manipulation, and you'll see these terms in there as well. But here's a stiffness matrix for a simple piece of pipe. It's a 12 by 12 stiffness matrix, and here is the response on the from end due to a displacement on the from end in the Y direction. So if I move this from end up and down, this term here gives me the amount of load I generate by moving it up and down based on the stiffness of this piece of pipe. Now, of course, there's other pieces of pipe connected to it as well, but for this piece of pipe, that's it right there. Now, what happens when I put a restraint in there? I put a Y restraint. What the program will do is it will add on this translational stiffness of that restraint. And now that's that 1.75 e to the 12 that we put in here. And now that node really can't move up and down anymore because it's so darn stiff there. So that's how we change the stiffness matrix to reflect this restraint. Now this is a linear restraint. That will always be in the stiffness matrix. But you see now that when we have a nonlinear condition, let's say the pipe wants to move up. Well, if the pipe wants to move up, we do not put that stiffness in because it's free to move up. It's only if it wants to move down that we put that stiffness in. So the program is always monitoring every node in the piping system where there is a nonlinear restraint and confirms that the way that the stiffness matrix is assembled, it reflects the true operation of the final position of that piping system. So again, if I have a non-infinite stiffness here, a spring rate, I will put in this stiffness in my stiffness matrix and it'll be linear. If it is a non-linear restraint, here I don't have this strap over the top of the pipe, it can now disengage so it can lift off. So here we have a situation where if it wants to move in the positive Y direction, there is no stiffness associated with that restraint, but if it moves in the negative Y direction, it will have to push the spring out of the way. So we have to handle the stiffness based on where the pipe is. Now the program will adjust the global stiffness matrix based on the status of every node that has a nonlinear restraint. So the program will get the final position of the node for that iteration and compare the stiffness that should be at that position. If it is matching, the solution is correct. If they do not match, let's say you have the stiffness in the model and it wants to lift up off a resting support, the program has to then update the stiffness matrix and run the analysis again. The program will continue to do that until all the nonlinear conditions applied in the global stiffness matrix are consistent with the calculated position of each point in the piping system. This process will have to be rerun for every basic load case in the analysis. We'll go in and take a look at the actual process that Caesar 2 uses in order to solve these nonlinear conditions.